So now we're going to look at one other example of systems that use interprocess communications. So Mach, of course, is the microkernel that is at the heart of Mac OS, which used to be known as OS X, um, or OS 10. And there are some very key characteristics of Mach which make it very interesting when it comes to interprocess communication. The first piece here is that the Mach microkernel is predominantly message-based. Pretty much most communications across the Mach microkernel are based on messages. So even system calls are messages. Furthermore, each process, also known as a task in this case, gets two mailboxes at creation, the kernel and the notify mailboxes. And then furthermore, really only three system calls are needed for message transfer. And these are message underscore send, message underscore receive, and message underscore RPC. There is a need for mailboxes for communication in the context of the creation of these mailboxes. It is the port allocate system call that is used there. So again, four system calls that are pertinent to this interprocess communication in Mach, which is predominantly message-based. The send and receive are indeed flexible, so there are really four options. If a particular mailbox fills up, what happens is you can wait indefinitely, you can wait at most n milliseconds, you can return immediately, or you can temporarily cache a message. So that was with regard to Mach as an interprocess communication system example. We, of course, looked at POSIX prior to this in the context of interprocess communication with an example of POSIX with shared memory. But in this case, this is definitely message-based for Mach. Let's move on. Let's move on to the third example, which is Windows. So really, we have covered three of the most popular operating systems, at least when it comes to desktops and servers. We started with POSIX from a shared memory perspective example. We touched a little bit on Mach and how it is very much message-based, and IPC occurs via these messages. And then now we're going to look at Windows, Microsoft Windows. So with Windows, there is more of an emphasis, at least with the IPC mechanism, there's more of an emphasis on communication within the same system. And there is this facility that is set up essentially called the Advanced Local Procedure Call Facility, which is available on Windows systems. Do note that this is not exposed through the Windows API, and really it works again on between processes on the same system itself. So again, on a given Windows desktop or a Windows server, ALPC is very much in use. It uses ports like mailboxes to establish and maintain communication channels, and kind of the workflow for this communication is as follows, right? So the client opens a handle to the subsystem's connection port object. Then the client sends a connection request. The server, in turn, creates two private communication ports and returns the handle to one of them to the client. And finally, the client and the server use the corresponding port handle to send messages or callbacks and to listen for replies. So that is, how this ALPC methodology works in Windows systems. Okay, let's move on. So this is again just a visual representation of what we just discussed with Windows. All right, so those were examples of interprocess communication in certainly Windows and in Mach. Now we're going to shift gears and look at client-server systems. So client-server systems, of course, can exist on the same physical box on a single operating system. You can have a client and a server, of course, or you can have these client-server systems that are distributed. So um, there are several paradigms when it comes to communications in client-server system. Sockets are a very popular and a dominant method there. We will discuss these in just a moment. Another method or methodology is using RPCs, or remote procedure calls. Another one is pipes. And then finally, there's also remote method invocation, which is a Java paradigm. So let's talk about sockets. So a socket is really an endpoint for communication. It is very much oriented towards network communication to the extent that it requires the buildup of a socket, or the instantiation of a socket requires the existence of a networking stack on a given operating system. So of course, in both Microsoft Windows as well as Unix systems, Linux systems, certainly on Mac, TCP/IP is the predominant networking stack, and sockets are nicely layered on top of TCP/IP as a networking stack. A socket, when we talk about a socket, is fundamentally just a concatenation of an IP address and a port. So it's an IP address, of course, being 4 octets, and then a port number which can range from 0 to 65,535. So that is what a socket is. It is a combination of an IP address plus a port. Many times they're represented as 4 octets, which are separated by dots, and then there's a colon to signify that that is the end of the octet, and now we're going to be looking at the port thereafter. So 161.25.19.8:1625 refers to port 1625 on the host 161.25.19.8. So communication when it comes to sockets always occurs between a pair of sockets. And just a quick piece of information relating to the way these ports are defined is that ports with values lower than 1024 are known as well-known ports. So there are well-defined standard services that are associated with these ports. So of course the most commonly known one being TCP port 80 is associated with, of course, a web server running on a given host. And if a client wants to connect to a web server, it connects on TCP port 80. So by default, all web browsers, when they connect to a website, they are in fact connecting to in the end, they're connecting to an IP address. It may start with a DNS name like www.txstate.edu, but eventually that gets translated through DNS to an IP address, and then the port associated with a web server, at least the well-known common port for non-encrypted web server communications is port 80. For encrypted communications, it's 443. As you can see, both 80 and 443 are under 1024 because these are well-known ports. And if you choose to come up with a brand new service that you feel should be offered using the TCP/IP networking stack, and there should be a new port number that should be assigned for it that is below 1024 and should be well known, then effectively that needs to be proposed in the form of an RFC, and eventually it can conceivably be adopted. One quick note on IP addresses. So there is a special IP address, 127.0.0.1, that is known as a loopback address, and that just refers to the system itself, the system on which the server is running. Will refer to itself as 127.0.0.1. So for test purposes, if you have a server running, again, if you're running a web server on your own desktop computer, and now you want to go ahead and connect a browser to that server, you would refer to your own server's IP address as 127.0.0.1. Sometimes you would also call it localhost, and this is all configured in the context of name services, domain name services. Okay, so socket communication, just a visual representation here one more time, just reviewing what we just covered on the previous slide. What we've got here is a socket where socket connection between 146.86.5.20 port 1625, so that is my source port, and I'm connecting to so making a connection to 161.25.19.8 on port 80. Okay, so that is, of course, again, the port for the web server. So I have a client, which is host X, communicating to a web server, and likely getting HTTP data with embedded HTML therein. Okay, so let's look at an implementation of sockets then. So sockets, again, being a mechanism for, a popular mechanism for client-server communication. There really are three distinct types of sockets. The first type is a connection-oriented socket, also known as a TCP socket when it comes to the TCP/IP networking stack. And TCP there stands for Transmission Control Protocol. It is a protocol that effectively builds a channel, a virtual channel between any two endpoints. Again, an endpoint, there's two endpoints being a client and a server, and it is connection oriented, as in you're maintaining state of a connection between these two entities, and then there's definitely error control as well as retransmission that is built into this mechanism of being connection oriented. The second type of socket is a connectionless socket that uses the UDP protocol. That stands for User Datagram Protocol. That is also very much part of the TCP/IP networking stack. And in this case, we are not connection oriented, we're connectionless. There is no state that is being maintained. There are no sequence numbers that are being maintained to make sure that every communication gets through. And then finally, there is a multicast socket class where data can be sent to multiple recipients. So a TCP connection is typically between two endpoints, a client and a server. Likewise, even a UDP connection, even though it's connectionless, there's a communication between two endpoints. With multicast, what we have is essentially one initiator of the provider of the data, and lots of subscribers that can receive the data that is being sent through. So one producer feeding multiple consumers at a given time. That is a paradigm that can very nicely be mapped using multicast socket connections. So on the right side of the slide, we see sample code for a socket in Java. So we are now seeing an implementation of a socket in a programming language. Here, of course, we've chosen Java as the programming language to illustrate this particular socket connection. And a few things to point out here are as follows. The first one is, so this of course is fairly easy to comprehend. We're just trying to create a new server socket on TCP port 6013. So server socket sock equals new server socket 6013. And then let's go ahead and accept connections on this socket. So that's what we do here with socket client equals sock.accept, right? Start listening for connections on TCP port 6013. And the next thing what we do is we go ahead and populate a print writer with the data that we want to publish on this port. And then finally, with the next statement, with the pout.println, we go ahead and write the data. In this case, it's simply a date that we're writing out to the socket. And then finally, we close the connection and we start listening one more time, right? So that's effectively the way this socket is manifesting on the system. Okay, we will now take a quick break for a demo.